So welcome everyone. Welcome to a different lecture than the other classes. So in this lecture, I will talk about chemical kinetics. Right. Previously, I have been talking about some basics of how to draw a plot, basics of function, how do a function look like that, like that. Things have been discussed. So I have already taught you guys like how a straight line will look like, how an exponential function, basic exponential function look like, basic equation of polynomial, how you can plot it. These things have already been covered. But today now I'll start another topic, chemical kinetics. These topics are deals with various equation and similarly various kind of plots are normally asked from the students. So this chapter uh, can be better understood if you have a prior knowledge of whatever I already talked, like how to draw a plots, how basic knowledge of function, basic knowledge of continuity. So this thing, if you know, then it will be very helpful for you, right? Now let's go into whatever is today's topic. So today's topic is chemical kinetics, right? Um, this chapters like chemical kinetics or thermodynamics or anything you think of spectroscopy, the kinetic theory of gas. These are some kind of theory, right? And this basic theories can be divided into two parts, right? The first kind of theories are like there are no assumptions, there is nothing. Depending upon some experimental observation, we postulate some rules, right, like that, and they are never wrong. So this is the first kind of theory, and experimental chemical kinetics is one of them. In thermodynamics is also one. And there are the second kind of theories. You start with some assumptions, like some assumptions, some postulate. You start with that. You start by assuming something, and then derive. So the success of this kind of theory depends upon how much right your assumptions are, how much uh, error-free your assumptions are. So one example is like if you think about quantum mechanics, if you think about statistical mechanics. So these are started by taking some assumptions, right? Explain that like for the chemical kinetics is divided into two parts. First, what is experimental chemical kinetics? So in that part, we normally contemplate how our reaction will go faster or slower, how much time it will take. Basically, the rate of a reaction we will discuss, and that part is mainly falls into the first, like first kind of first category theory. So which is based upon the experimental observations. Okay. And the second part of chemical kinetics is rate theory, the theory of the rate of reactions. That based upon the assumption kind of theory. Right? Now, if you think about any chemical reaction, right? Any chemical, it has three aspects. First is feasibility. Feasibility. So what does that mean? Feasibility, or you can say the possibility. मतलब एक reaction अगर होगा या नहीं होगा, ठीक है? That possibility, that is called the feasibility of a reaction. मतलब like there are if you go to one laboratory, right? Go to one lab and you just take A, some chemical, and B, some other chemical, and mix it. Will there be a reaction? Will there be a reaction or not? Right? You need to know that because if you think right now, I am having one pen. So this pen is some chemical, and I am adjusting of something. This does not react, right? That's why this is like inert, and we can do whatever we want to do with it. But if it reacts, so then there is no point of having this. So that is the feasibility. So when a reaction will happen, when a reaction will not happen, and that is mainly dealt by thermodynamics, chemical thermodynamics, right? Or you can call thermodynamics as well. Now, let's say the reaction is actually occurring. Then, how much you will get the product? If you think about A to B, let's say A to B. So, if you start with, let's say, 10 gram of A, how much B you will get? It's 3 gram, or it's 10 gram, or it's 1 gram. You need to know, because let's think about any industrial reaction, right? Like industrial reaction should have the quality that it transform as much as possible. So if you start with 10 gram and if you get only 1 gram or 3 gram, then obviously this reaction is of no use, because it will more of the starting material will be there, the mixture of products, so many problems will be there. So the how much extent a reaction will go is very, very important. That is called extent of reaction. And that is mainly comes from equilibrium. But let me tell you, these two are not something different, because these two are same. Because if you know about equilibrium constant, that is K, it is always right. It is delta G down, that is purely thermodynamic. So this both of the things has been actually determined by thermodynamics. Now the third question. Let's say the reaction is actually occurring. Now we need to know how much time it will take to complete the reaction. Because you need to know, otherwise, if the reaction is a 1 year reaction, right? This reaction is not that kind of fast. Let's say for graphite into diamond, right? It's a very, very slow reaction. So that you should know. That is the dynamics, or that is called as speed of the reaction or rate of the reaction, right? And that is dealt in kinetics. Kinetics means the study of like the speed, or like that. In physics also there's a chapter that is kinetics. So that is how fast a reaction will be. That is discussed in the section of chemical kinetics. Let me give you one fast example, a fast reaction example. Um, Many of you will have done, have already been done some titration, acid-base titration kind of reaction. So there you take phenolphthalein indicator and you put, whenever you put the acid into that reaction, whenever the drop is falling down, there then and there a color is generated, right? So it's a very, you think like just the drop is actually coming and color is generated. So it will be very fast reaction, obviously. There are many such reactions which are very, very fast, which are very, very slow, which are very medium. So depending upon that speed, normally we generalize chemical reactions into three parts. One is very fast reaction. I'm writing reaction as RX just this is a denotation method. This is not the actual spelling. The big one is very fast reaction. Second one is moderate fast reaction. The number three is right. So if you think about some example, we already talked about very fast. What is the acid base reaction? Right, acid base reaction. This is very fast reaction. One of the very fast reaction. Moderately fast reaction is decomposition of hydrogen peroxide. There's ester hydrolysis. This is also part of practical syllabus in BSc chemistry, right? Because uh, this reaction is moderately fast. If the reaction is very fast, you cannot determine the rate and all. And if it is very slow, so in a day you cannot perform the reaction. So to measure rate of the reaction in a practical curriculum, we always choose that moderately fast reaction. So one very famous practical is like ester hydrolysis. Both the acid and base catalysis, these are moderately fast reactions. Now very slow, you already know, everyone has seen that. What is that? Roasting of iron, right? Very simple. If you just throw one iron outside of your home, when after some days, like 17, 12 days, you will see some rusting, correct? If you think about radioactive reactions, these are also very slow reaction, and because it takes much longer time. If you like just recall about the radioactivity problem, the half-life normally they give in some 35 days or 200, 2000 days, kind of like that. Some like with the help of radiocarbon dating, radioactive carbon dating, people normally find out the age of a stone, age of a like fossil, like that. So that means radioactive reactions are such. Right? So these are some example of how a reaction will be. Okay. Now let's say how a typical reaction will look like. Right. Typical reaction normally look like A plus B to some C of C plus D of D. And this small a, b, c, and d, these are called the stoichiometry. Of the reaction. This is called the stoichiometry of the reaction. Now, how fast or how slow a reaction will be will depend upon the concentration of that is the reactant. Okay. So now we are not right now. We're not talking about the order. We'll come to that. बट कितना फास्ट हो कितना स्लो हो इसके लिए कि रिएक्शन को रेट कैसे मतलब you can express it. We need to know that, right? Now, to know that, you just think like that. Their rate is nothing but the speed of the reaction. So, after a certain time, how much it is going. Okay, let's say at certain time, let's say after starting a reaction, after 5 seconds, what will be the concentration of your reactant? That is nothing but the at that moment, that is the rate, because rate will be what? It will be some concentration change, whatever it is, change by time, right? That is the unit time में कितना होगा. That is it. And this rate is normally can be of two types. One is average rate and average reaction rate. Another one is instant reaction. Right. Now, what is average reaction? Let's say, let's say ashram. You know ashram, or let's say chahal. कल ही बॉल किया था फाइनल मैच में. तो चहल बॉलिंग कर रहे हैं और उन्होंने T20 में 4 ओवर को बॉल मारा. उसका जो पहला ओवर था, पहले ओवर में उसने दिया 10 रन, सेकेंड ओवर में उसने बस 2 रन दिया, 1 विकेट ले ली, थर्ड ओवर में उसने 7 रन दिए और फोर्थ ओवर में उसने ज्यादा होता है लास्ट ओवर मार तो 16 रन दे और 3 विकेट। तो कितना रन वो ऑन एन एवरेज चहल ने खाया, अगर इफ यू वांट टू कैलकुलेट, इट इज वेरी सिंपल। You will just take the total run he conceived, that will be nothing but 26, 28, 35, right? 35. Just for the sake of it, just say it is 8. It is 36. And how many over? That is 4. So what is the average run he conceived? It is 9 per over, right? Per over 9 runs he conceived. But if you think, like if let's say somebody asked 9 run means on an average her over means the run he conceived is 9, but at over second over just conceived 2 run, at fourth over he conceived much more run, 16 run. So this average rate is not giving the proper right picture. Okay, that's why if you know the exact, like if you know how many runs he conceived in the second over, that information, that is the instantaneous information, right? Instantaneous information. And this on average picture, if you are getting, that is on the average picture, like average rate kind of thing. So if you think about any kind of reaction, let's not go into the rate like order and all, but if you think about any kind of reaction that is converting from A to B, right? From A to B. So let's take an example of a reaction, what we were talking about. So at initial time, right? This is your reactant. So at initial time, that means 0 time. There should not be any B, any product, right? Product B. That means at T is equals 0, A, the concentration of A will be there, but concentration of B will be 0. Let's say concentration of A is A naught, but B will be 0. With time, this A naught will become kind of A at any time it, and this will become VT, right? Very in a very generic sense, if you think what will be the plot of concentration of A with time, and let's say concentration with time, concentration of B. That means nothing but the product and reactant. At 0 time, the reactant is having the highest concentration, that is the initial concentration, and we define this as AG. And with time, this should decrease. Right? This should decrease, and sometimes it should be zero. Don't think about any kind of order or something, but the initial, the trend, the normal trend of concentration of reactant with time should be decreasing. It should decrease with time, right? And similarly, at time 0, there will be no B, there will be no product, but with time it should increase in a similar fashion. So product will decrease, sorry, reactant will decrease and product will increase. Now this, in this case, if you think about any two time, let's say this is your time T1 and this is your time T2. So in between this time, whatever the concentration change is, let's say this is your C1 and this is C2, will give you some rate of the reaction, because rate of the reaction is nothing but change of change of concentration with respect to the time, right? Change of concentration of a reactant or a product with respect to the time. So this rate you can write it like C2 minus C1 because it's initial by final, and you can write it like T2 minus T1. So if you think in DLC and delta, so this is like over a period of time. If you think about the last example, the 4 over of charge. So this is over a period of time of 4 over. This is over a period of some time T1 to T2. That is called delta T. And this is called as average reaction rate. Right? For this case as well, if you think at time T3 and time T4, let's say this one is C3 and C4. So in that case also you can write the rate. This is not the rate of A or rate of B. This is I'm talking about overall rate of the reaction because something will decrease, something concentration will increase, and similarly something will increase. Okay, so you can express it with express it in either of the terms. That is what we're talking about. Now, if you express it in the terms of product, that time as well the rate will be C4 minus C3 by T4 minus C3, and that time also this will be delta C by delta T. This is also some average reaction rate. Now let's just think the C2 is lesser than C1, and in this case C4 is greater than C3. So this term, this delta C for this case is negative, and this case this is positive. So that's why that is the common practice is whenever we are expressing rate in terms of product, you normally write it down as plus del C by del T kind of, and whenever this is for reactant, we will write it down like because reactant is actually it is getting destroyed, or you can say like for if you write it down in terms of reactant, we normally write it like rate of this of reactant in this case this will be minus delta by delta. Okay. Now if you think what will be the instantaneous? Instantaneous, we already said what is instantaneous? Instantaneous nothing but at any given point of time, what we do. Let's say this. So if you write down a slope and this is this at this time t, what will be the rate? Normally this is called like this. There's a difference. There comes a use of derivative. And normally write down instantaneous rate is like minus dA dt. In case of delta, we write derivative, and because of product, let's say B, that is product dB dt, that is price. Right? So at any given point, that is instantaneous. So obviously, for a case of like if you think about rate, this instantaneous rate of reaction is much more useful because we just take the example of that volume of charge again. So you need to know at certain point, like after 5 seconds, how much reaction is, and how much reaction is still left, and after 10 seconds, how much reaction is like that. At any given point of time, what is the reaction? That is instantaneous reaction, right? Now let's give us the we take a real example. Into plus 3H2 to NH3. all the species that in nitrogen is in gaseous phase, this is also in gaseous phase, this is also in gaseous phase. So whenever all the species of a reaction are in same phase, so then we call the reaction homogeneous. If any of the species is in different phase, any of the species is in different phase than the others in the reaction called as right. So this is purely homogeneous. Just for information. Now, if we think about this reaction and try to write down the rate of the reaction in terms of reactant or product, right? So what will be the rate of the reaction? Now, if you think about this rate of appearance of N, right? It will be minus d of into concentration I'm talking about by dt, right? Disappearance of, if we think about hydrogen, it will be minus 1 by 3 d raised to dt. Why is this so? This is just try to understand it by simple analogy. So whenever if there is nothing, that means it is one. So whenever one molecule of nitrogen is disappearing to form a molecule of ammonia, that means 3 molecules of hydrogen is going. So if you think the rate for this rate for disappearance of nitrogen, let's say it is X, that means at that time 3 molecules, that is much faster, is going on. And if you think this is Y, so Y will be equals to 3 times of X, right? It will be equals to 3 times of X. That's why it is like that. So the general procedure is, I already said, whatever is the prime number, the number are before the molecules in a chemical reaction, in a balanced chemical reaction, are called as stoichiometry. So you need to divide the stoichiometry to get the rate of the reaction. So for in case of hydrogen, it will be minus 1 by 3 dH2. And from, if you just, because this is the rate of the reaction, rate of disappearance of is nothing but rate of reaction. This is also rate of reaction. So you can just equal these two. So something not expected, and it happens several times during the video. So pardon me for that as well. So let's say this is the same reactions rate. So this two will be equal. Let's say this is X and this is Y minus 1 minus 2. So Y is equal to 3. So rate of disappearance of nitrogen will be 3 times of that. rate of disappearance of hydrogen will be 3 times of that. So similarly, if you write down this rate of formation, because ammonia molecule is formation of NH3. If you try to write that, it will be equals to 1 by 2. Now we said already for any product as it is forming, as the concentration difference is final minus initial is positive. So we give a positive sign there. And the stoichiometry divided by d NH3 right? DNST. So this is a practice of writing reaction rate. Now, now we know like what will be the parameters that will affect the rate. The rate depends on first the temperature. We said these theories are based on some experimental observation. So we know that any kind of reaction can be made fast by just heating it down, like increasing the temperature. Normally, with increasing the temperature, rate of reaction increases, right? The temperature, similarly pressure, right? If any kind of presence of a catalyst can alter the rate, then if the catalyst is similarly obvious inhibitor, difference between catalyst and inhibitor are someone catalyzes or make the reaction faster, someone actually hinder the reaction kinetics. That is called inhibitor, right? Now, if it's a photochemical reaction, that time the intensity of light similarly electric field, electric and magnetic field can have the effect on the rate of the reaction. So these are the things on which rate of the reaction normally depends upon. Okay. And for any kind of reaction, the rate can also be written as the concentration raised to a certain power proportional to the concentration of reactant raised to a certain power. So if your reaction is A to B, so we can write down rate as rate will be equals to proportional to concentration of A to the power something to the power B. Let's say. Right. So for this is actually think of not the concentration, this is actually think of the active mass. For any diluted system, diluted solution, the concentration and the active mass is same. That's why I am writing it as concentration. So for a typical kind of reaction, A plus B to C plus D, we can write the rate is equals proportional to A to the power some alpha, B to the power some beta. This has nothing to do with this power has nothing to do with the stoichiometry. These are different. If we want to write down the rate of a reaction in terms of the stoichiometry, that is different. But whenever we are trying to write the rate of a reaction in terms of the concentration of reactant, that in the power, whatever it is not the stoichiometry. That's why I made it different. This is alpha and this is beta, right? So from that you can write that rate is equals some constant K, concentration of A to the power alpha, concentration of B to the power beta. Right. So this is a rate equation as well. Now, so if we just mark these two, we can get rate of a reaction is equals, let's say, in terms of A minus 1 by A D is equals minus 1 by b dv dt is equals plus 1 by c into c dt is equals plus 1 by d dv dt, right, is equals k, it's a concentration of a to the power alpha, concentration of b to the power. I'm telling it several times. This is A, B, C, and D have nothing to do with alpha and beta because these two are different. Now, what is alpha and what is beta? So alpha is the order of the reaction with respect to the there is some I species. Beta is the order of the reaction with respect to the different species. If it is the I species, it is the Z species. Right. So these are alpha and beta. And overall rate of the reaction is equals alpha plus beta. Right. So if you ask that what is the rate of the reaction with respect to A, that means it's alpha. What is the rate of the reaction with respect to B, to be beta. But what is the overall rate of the reaction? That is alpha plus beta. So we need to know what is the order of the reaction. What is the definition of order of the reaction, right? What is the definition of it? Rate. Let me first write it down. Then I'll discuss. Rate of reactant at the particular rate forms these powers are called of so what does it say? The rate of a reaction is proportional to concentration of the reactants at that particular time. When you put whatever time you are talking about, that is the instantaneous rate I am talking about. So at any particular time, whatever the reactants are, okay, these are the points, reactants, and at that particular time, raised to a certain powers. Okay, so rate can be written as the certain powers of the reactant at the reactant concentration at the particular point of time. So that certain powers, these are purely experimental parameters. Okay, you cannot predict what will be the rate of what will be the order of the reaction. This is purely experimental parameter, and that certain powers are called order of the reaction. So if let's say A to B is happening, and rate can be considered as K A to the power N. For any kind of reaction, then An is equal to order of the reaction. Order of this reaction A to B. But that's called stoichiometry. Let me say it again. Stoichiometry, maybe this is 1. So it doesn't depend upon the stoichiometry. This order is purely a experimental parameter, right? So this order can be of various types. As I said, this n. If this n is equals 0, then it is called 0 order. If it is 1, the 0 order reaction. Then if it is 1, it is first order. If it is 2, it is second order. Similarly, like that, it will be nth order reaction. And for any kind of reaction, we need to know how we can express that rate of the reaction with respect to time. We can know how that reactant concentration will vary with respect to the time, how the concentration of the product will vary with respect to the time, and that is the main topics to be discovered, to be discussed in the upcoming lecture, right? So up to this, we learned why chemical kinetics is important, what are the main 3 aspects of a chemical reaction, and what is the chemical kinetics among that. We know that. Now we know that how to write a rate of reaction, what is the basic difference between average rate of reaction and instantaneous rate of reaction, and how differently we can write it down, and for any given kind of a reaction, how can we write down the differential rate equation, right? So whatever we have learned, that is differential, that instantaneous rate reaction, how we can write it. So up to that, I think this much is okay. So you read, you just see the lecture, you read any book for these kinetics. You can go through K Kapoor book, and also for better like understanding for the high level, you can see the late level book as well. Okay, so study hard, and we will meet in the next lecture. And that time I will discuss about India's order reaction, starting from 0 order, first order, second order, and then nth order. And now after that, we will talk about some complex reaction like parallel reaction, consecutive reaction, and so thank you very much for listening. And see you soon in the next lecture. Okay?